Today, I will just wrap up this series on use of the free. Not so much on reference counting actually, but since that was what we were talking about, so I will also count this as wrapping up that one. I think I originally wanted to present about more bugs, but I think those are too complicated already. Very hard to present also. So I think never mind. Okay. Uh, Today we will look at a few. Today's plan is to look at programming languages that are other than C or C++, because in the past many sessions I was covering in C++, because in C++ we have to manage memory ourselves by calling malloc or free or new or delete ourselves. The programmer has to manage everything himself because C++ is a systems language and it is supposed to give the programmer all the control so that it can be very fast if the programmer is good at making certain optimizations or decisions. So C++ gives all the power, but then we have to be very careful. If not, it is very easy to make bugs due to poor memory management. Then, on the other hand, other programming languages such as uh, Java, JavaScript, Python, they all, sorry, Java, JavaScript, Python, they all have we never need to manage memory ourselves because under the hood there is a garbage collector. And now let's look at a few. I've collected a few links which are bugs in the JavaScript engines. So even though JavaScript has a garbage collector and we don't have to manage memory ourselves, there is still a chance of uh, use after free because of certain mistakes in the engine itself. So let's look at some examples. So this one is the first example, a use after free in Adobe Reader. So Adobe Reader, I'm not sure if you all are familiar. There is a JavaScript engine inside Adobe Reader. Same for Foxit Reader also. And usually these JavaScript engines are older versions of some existing JavaScript engine. I forgot which one is this already. Maybe this one is Spider Monkey or uh, I forgot which one this uses. Adobe Reader uses an engine based on Mozilla's Spider Monkey. Spider Monkey is Mozilla Firefox JavaScript engine. And then they modify a bit so that they can support this thing called the eScript API, which is their own scripting API framework, scripting framework in Adobe Reader. Let's see, there's another one, Foxit Reader. Foxit Reader uses V8, so from Chrome. Yeah, so they all have a JavaScript engine inside, but they don't write the whole engine themselves because that is too much effort really. That is too hard. It's better to just use an existing engine. But let's see what's wrong in their own additional stuff. Uh so they made some mistakes here. So let's look at the uh data structure here. So here eScript is just Adobe Reader's JavaScript scripting framework. So they have this thing called ES objects, which is eScript objects, which is somewhat related to JavaScript objects. And then they have this thing called object cache, so that it is used so that you see when a data blah blah they basically keep a pointer in the object cache instead of performing a new allocation. So this is the main idea. They keep a pointer in the cache instead of performing a new allocation, which is slower. Okay, the only I think it's quite hard to understand because there's not enough information. But if you move forward, this ES string has this kind of structure. So what type, and then the string buffer, the contents of the string, and then some length capacity. So the problem here is that when the ES object is free, this pointer in the object cache is not removed. So as we are should be quite familiar with now, if we have a pointer that is stored somewhere, and then the underlying contents is free, then we should delete this point, remove this pointer from anywhere so that no one can use this pointer anymore, but it's not removed. And then it becomes stale. Stale means yeah, not fresh. Means yeah, it's old already. It shouldn't be used anymore. And then the issue arises when this ES object pointer is in the object cache, and then oh yeah, this is the reason. But we'll skip this for now. If you're interested, you can read it yourself. Basically, there is some they do some checks of the type, and then yeah, the type is unseen. And then when deleting an ES object pointer entry, the type that they use to search for entry to delete is Unicode. So different types, causing the something not to be deleted. Yeah, so it's a logic issue in their engine. So let's see how the POC looks like, which is quite straightforward, simple. And in the past, there are a lot of use after freeze in JavaScript engines with this kind of simple POC, but now it is almost not possible to see this kind of very simple POC already because they fixed all of them. Yeah, so I'll go through this and you'll see why is it so simple. So to trigger this bug for this function, and then so step one, you create an object, and then the pointer is stored in the object cache. And then here it says remove the reference to the object. So it's saying that inside here is not pointing to this anymore. So no one has a reference to this anymore. So it's a bit like reference counting, but it's not. There's no counting. It's just no one has a reference to it. And uh yeah, so at this point the address is still in the object cache. So in sys runtimes with garbage collection, we don't need to do reference counting because there's a garbage collector. So the basic concept of a garbage collector, we will look more into it later. But the basic concept is it will scan the whole heap, and then it sees which object is still being held by other objects. For example, here this object that was supposed to be held by data object 0 has no more reference now because we remove the reference. So now we set data object 0 to now. At the start, it was supposed to be some value, some object, but now it's now. So here it says trigger a GC. So how to trigger a garbage collection run in JavaScript is very dependent on the JavaScript engine. For example, with Chrome, maybe it's you allocate and delete many objects, then it will trigger a GC. So I'm not very sure what is the trigger for GC in Adobe eScript, but it's not so important. To you just normally people will just use the same way to trigger it, then you just reuse the same technique. So what happens here is you set a timeout, and then this timeout after I think is 1000 milliseconds. So after 1 second, call this function, trigger UAF. So a lot of JavaScript exploits in the past are in this format. You set use a function that will call a callback. Then when this function is called, the flow is like this. Okay, let me see how to. Okay. Uh, yeah, the flow is like this. We our code is here, and then after that, the code program continues. But we have a callback, which is this function. Oh, actually, let me zoom in a bit. Our code is here, and then because this one is a timer callback, so this one will not be called now. It will be called later. And then when the program continues, maybe it decides to call the GC, the garbage collector, and then free the object. And then the program thinks that, oh, everything is okay. But 1 second later, this callback gets called, and then it uh, access this thing that it was freed already. So this one is supposed to be freed, but because the pointer is still inside the object cache, so it there's a use after free. Then depending on how you can manipulate the contents of the object, then you can write an exploit. So okay, here are some debugger output, which I think we skip. And here, yeah, here's an exploit technique, but I won't cover this here today because I think we need more basic knowledge of the V8 internal structures first to be able to understand. Okay, this is actually not the typical kind that I wanted to show, but uh, there's another kind of use after free, but I couldn't find an example, so maybe it is not so relevant anymore. But I will just show. So it is like this. It will be something like this. Like function, and then some callback. So what happened is maybe when you call a function, the function will do something and then call this callback. And then maybe this callback will free some objects. But because the function doesn't know about it, then the engine also didn't manage to handle the memory management properly, then function will have a use after free. Something like this. But I think sorry, what I say is not very clear, but I couldn't find the example. Okay, now let's look at the next one. So here is one more. This sorry, this was the one that I wanted to show that uses a callback. So this is in Internet Explorer JScript, but now you know that Internet Edge, they use Chromium underneath, so they don't use their own engine anymore. But let's look at this bug from 2019 and see how it works. So the flow is basically something like this. You have an object and then call a function with a custom callback. So sorting, it will do something here, but sorting, it will also call this callback. So we need to check what does this do. So this JavaScript sort function, it takes a function that compares, that can take in two values, and then you return should be this. Yeah, return a number to say whether they are equal or different, or which one should come before which one. So I think if we have written some programs before, we should have seen this before. So you sort with a compare function. So here we give it a quite this kind of compare function that obviously doesn't do any comparing, but does something malicious. So the to really know what is sort doing, we need to you need to look at the source code of the JavaScript engine, but never mind, we don't look at this today. We just look at the idea. The idea is when the underlying engine wants to handle this sort function, it will call the callback on the elements of the list pair by pair. So since here we only got one pair, so we think of it as f paired with one or two, one and two. Then let's see what happens inside f. F will create a lot of objects, and then store one of them in arguments 0. So if you are not familiar with arguments, it is a special object that is the it you can access the arguments of a function through this arguments variable. So you see like this. Argument 0 is A, arguments 1 is B, arguments 2 is C. It's the same thing. So in this case, okay, let's look at this example, but we don't call this. See, so arguments is an array with two elements because this custom compare function should be expecting two elements. So it's not really an array, it's an object because I think then you can have default arguments and all these things. Anyway, here we do some so this you see usually the engine they don't expect this kind of things to happen, and so maybe they miss out the possibility of this kind of very unnatural things happening. For example, setting the first argument to be to track one of the objects here. But it turns out that this arguments array is not tracked by the garbage collector. So just now I will recap what the garbage collector does. The garbage collector will look at the heap and then it scans through everything inside. And then it checks which one does not have any reference anymore. So no one, it checks each object and see, oh, is any object still holding a reference to this? If not, then we can free this one and check this one. Is there any object holding a reference to this? Then maybe yes, then we move on. Then this one, is there any object holding a reference to this? Then if no, then free this also. So let's look at this. So this is how V8 does it, but the concept is most likely the same for most garbage collectors. So it is called mark sweep or mark compact, something like that. So usually it's like they start with marking. So they mark, find out which objects can be collected, means free, which one can they free. And then sweep means they just sweep all the objects that are dead to the free list. So we have looked at the free list in C before. Then okay, this compact is just like defragmentation, just like hard disk defragmentation. So later we will look into this for the next write-up. Now we come back to this one. So we hold a reference, but there was a mistake because this arguments array is not tracked. by the garbage collector. So here we try to uh, remove the reference to these objects, because you see, for each I, it holds an object. But now we set it to something else, then all of these objects that were here, there's no one holding a reference to them anymore. So when you call this collect garbage, so again, like just now, this inside here, it does some things to trigger certain conditions that make the engine do garbage collection. So this you can just treat as a black box for now, for our purposes. So after you garbage collection happens, all these variables get reclaimed or freed. So usually we say reclaim or collect. They get reclaimed, but you remember argument 0 still hold uh argument 0 still hold a reference to this. So we can use after free. Okay, so actually maybe it's not so necessary to use sort. Maybe you can use any function, because the bug is with arguments, not sort. Let's see the vulnerability details. So VAR capture. Yeah. So some variables are not properly tracked. In this case, so in this case, it is the arguments object during the array sort callback. So maybe it is related. It must be the array sort. Yeah, let's look at the fix. Okay, so the variant analysis. So variant analysis means they look at other bugs that are very similar to this one. So they know about this, then they try to find similar bugs that are very same. So here got VAR modified. Okay, similar to this. Yeah. Oh, this one. Oh, these are fuzzing. Not so important. Yeah, they found this. Use after free where members of the arguments object are not tracked during the toJSON callback. So here is the array sort callback, and then here is toJSON callback. So it should be specific to this function. Let's look at the fix, so that, oh, never mind. Maybe there is no fix. There's no open. It's not open source, because I don't know if where is the source code of Internet Explorer. Yeah, not very sure where is the source code. Let's see if we can find the source code for Internet Explorer. Actually, I'm not sure if, oh, it's not open source. Never mind. So, there's nothing we can see. Okay, now we look at one more bug. Now this one is in the garbage collector's logic, so more complicated. We just briefly look at the vulnerability. You see the POC is very long and very complicated. So we will not look into this. Just look at the idea. So back here, okay, we'll refer to this when we need. So the idea is during the garbage collection run, there are objects that the garbage collector will scan through objects and then record which ones are still alive or dead. So they mark. So for objects that still have a reference to it, they will mark it to say that it is alive. See here, liveness. So marking is the process by which the reachable objects are found. So any object that can be that has a reference by other objects will be marked. And then here the mistake is that the V8 garbage collector, they didn't mark some live objects. So it is for this weak map and weak set. Yeah, I won't go into this. But the patch is kind of, if you just focus on this part, the fix is mostly just this. So before you see that the fix is they see if they need to run the whole GC run one more time. So it's probably that running once is not enough because of this weak map and weak set things that maybe running once is not enough. So in here they explain it more. If you're interested, you can read it yourself. Yeah, then the fix is just to run again if you need to. So the conclusion is, even though there are certain languages, or specifically JavaScript, as a garbage collector, it is also not safe, not necessarily safe from use after free bugs, because maybe the underlying engine had some wrong assumptions about the objects, or the garbage collector has some bug. Because actually, if you think about it, the garbage collector is quite complicated because it needs to check every object and see if there's still a reference to it. And you cannot just do brute force search. That will probably, your browser will hang, it will take very long. So they have to do some smart way to find it. And they here, I believe they sort of make a graph. Yeah. So they have a route, and then they follow some pointer over and over. Then so they start with a set of known pointers, and then they follow each pointer to an object. And then inside this object, they check every pointer in the object, and then they just keep following until they think that everything is marked. But maybe there are some mistakes and you forget to mark certain pointers. Okay, so this is all for JavaScript. Now, the second part of today's session will be on Rust, which is, I think everyone here knows Rust. So I'm not sure if everyone here used Rust before. So the goal will just be to show some examples and to show this ownership thing in Rust, because the main point of this is to prevent uh, memory bugs like memory corruption bugs like use after free or double free that we have covered in the past few weeks. So Rust, they design the language such that when you compile the program, you will already know whether it will have very strict checks, so that during compile time, it will already prevent you from writing code that will have use other free or double free. So any code that you compile from Rust will not have these bugs. So let's see how they do it. So here is I will just go through this document and then highlight the raw do a summary of this by highlighting certain parts. So here it says, you see, some languages have garbage collection, and some languages you must allocate and free yourself. So we have looked at these two together already. Now Rust, they have their own approach. So memory is managed through a system of ownership with a set of rules that the compiler checks. So if there are any mistakes, then the program will not compile. And they design it so that it will not slow down your program. But it's very hard to write code that follows these rules. I tried before and I really cannot write Rust code. It is impossible. So this one, since we have covered last time, I will skip. And the rules are something like this. So each value has an owner, and there can be only one owner at one time. And when the owner goes out of scope, means when you exit, so you know scope is anything that is in curly braces, you mark it. A scope is normally denoted by curly braces. So for example, your function scope, your for loop scope, and so on. When the owner goes out of scope, then the value will be dropped. Drop meaning that it will be free. So here are some examples. So here, let's say here we have a scope. And then when you have a string object, it will only last in this scope. Meaning that once you go out of this scope, you cannot use this S anymore. So actually this still sounds quite normal because most programming languages are also like this. In a scope, you cannot use a variable that is declared in the scope outside the scope. So okay, so this is still quite similar to other programming languages. So now let's continue. So here we just concentrate on the parts that relate to ownership. So in Rust, there's a bit difference from this and this. So this one is called string literal because it's a hard-coded string. But this one is a string object. You see, string literal, they are convenient. So like just now one, but they are not suitable for every situation because they are immutable, so they cannot change it. It's a constant string. And yeah, maybe we want to have a string, like in Java string or Python string, you can modify the string very easily. So this is this big string. And because this string is maybe you can be longer or shorter, the size is not determined. So as I hope you are still familiar with heap versus stack. Since we don't know the size, we will allocate it on the stack. On the heap, sorry. Allocate on the heap. And then we can store an amount of text that is unknown to us at compile time. So if you know the size at compile time, then maybe you can put in the stack instead. You put on the heap when we are not sure of the size. That's why it is dynamic memory allocation. So blah blah blah. Okay, so here is still an example of how this string we can modify, then can append, then can print hello world. So here is still not so much about ownership, but let's continue looking at this to understand this data structure better. So this big string can be mutated, but literals cannot. Why? So in the case of a literal, we know the contents at compile time, so it's hard-coded already. And that makes it fast and efficient because they can put this string at a place that if you put in the heap, then maybe you need to find the pointer and so on. But okay, this is not a good explanation, sorry. If you okay, normally hard-coded strings they are put in the data section, and then all the accessors they have a hard-coded. The addresses are already known in the data section, so the code it will directly access the data section to read this string. But if it's in a heap, then at runtime, or at compile time, the binary that is generated will not know the address of the object in the heap yet because we don't know. It's dynamically allocated. So there's one extra step that is needed. You see, we cannot put in the data section a piece of text that is unknown at compile time or may change. So we need to allocate on the heap, which is something that we have seen before already. So in our way of doing it, in C, we malloc ourselves and allocate ourselves. In JavaScript that we saw just now, we need to return or let the allocator reclaim the memory. So you see, the first part is so the first part is they are also doing this. They manually requested the sorry, let me repeat. Actually, let me repeat just now what I say is wrong. So to allocate this string type, we need to request from the allocator. So this is like malloc. Then at the end, we need to return this memory to the allocator. So there are two ways. One is reference counting, which we manually return memory to allocator ourselves, or with a garbage collector, which is with mark, something like mark and sweep. And usually, and because Rust is a system language, I think it doesn't want to use a GC because any program with a GC is generally slower. GC is a quite complex a process. So yeah, they don't want it to, if you forget to pre oh no, oh yeah, so in most language without GC, you have to identify yourself, which is through reference counting. Or if you don't reference count and free, if you don't free it, then you waste memory, like what I have shown last time. Or if you free too early, then you have use after free. Or if you free twice, then you have double free. So we have seen all this before. So the key thing is to pair exactly one allocate with exactly one free, not not too much and not too little, exactly one at the right time. So their compiler, they basically just free right after at the end of a scope. So in C, you have to free yourself. So this thing doesn't happen in C. And in Java or JavaScript, this doesn't happen because the garbage collector will scan through at its own time, not at the end of a scope. So this is their own way, Rust way. This was, I guess, is a quite natural time to return the memory to the allocator. And they call this function drop. Rust call a special function, which is called drop, which is just similar to free. So in C++, there's this thing called RAII, which means at the end of the scope, they will deallocate. So something like that, if you are familiar. So now let's look at the more complicated things. With this thing a bit, I think they call it move semantics. So this one, nothing special. We are familiar with this. But let's look at the string version. So you see, normally, if you write this in Python, very straightforward, right? You create a string, and then another variable equals the string, means you copy the whole string over. Or in Java, I think in Java, if you do this, I forgot already, if you copy the reference or copy the whole, or you deep copy, yeah, I forgot. Or in C++, if you do this, it will be a shallow copy also. So different programming language have different ways. But here, let's see how what Rust does. It under the hood, let's look at what happens under the hood first. So you see a string is made out of pointer to the contents, length and capacity. Quite similar to what we saw just now with the ES string also. So most of the string objects look like this one. Very natural. So the part of the left is stored on the stack. I think because this one can be determined at compile time. But the contents of the string and its size, you cannot determine at compile time, so it must be in a heap. Yeah. So here we see it says that when you do S1 equals to S2 equals to S1, the string data is copied, means copy the pointer, the length, and the capacity on the stack. Because S1 and S2, they have their own this data on the stack. But actually, we just copy these three values only. We don't copy this whole data. We just copy it. So it's a bit like shallow copy. But it's also not exactly shallow copy because part of it is being copied also. You don't just copy one pointer, you also copy some metadata. So a half-half hybrid approach. So here, on the other hand, if you also deep copy the contents, then it will look like this, which is not what Rust does. Yeah, so it will be very expensive because you need to copy a lot of things. So here it says, earlier we say when a variable go out of scope, it automatically calls the drop function and cleans up the heap memory. But there's another thing, which is when two data pointers point to the same location, then how? Because there are two variables pointing to this, then at the end of the scope, should we free both or should we free one of them? But the freeing is, the code for freeing is generated compile time. So when you generate the binary, you already put in a drop pointer 2 and drop pointer 1. But if they both point to the same memory, they get double free. So Rust, they want to make things simple. They don't want to check if two point to the same memory because that might be quite complicated and a lot of unnecessary checks. So they have this rule. They don't allow you to do this at all because they, okay, this error is error borrow of move value, because you see when S2 is assigned to S1, S2 is now the owner for it. I don't know what's the exact word they use, but here they change owner. And then when you want to access S1 again, S1 is not the owner of this string anymore. So they say they want to borrow this value. The print line wants to borrow S1, the object in S1. But S1 does not own this anymore. S2 owns this. So it cannot, print line cannot borrow S1. Okay, let's see the explanation here. So you see, after doing S2 equals S1, it just invalidates S1. So it's known as quite a move. S1 move is moved into S2. You cannot, S1 is dead already. So by doing this kind of move, they will generate code that doesn't do double free because they generate code that the code already knows that S1 doesn't hold anything, is invalidated. So they only need to generate code to free S2. That's the whole compiler can know this because of these rules. Okay, yeah, so this is the basic idea of ownership. And yeah, here are more examples, but I will not go through them because it's 9:50 soon. But the summary is they have this concept of ownership means that you have to write code that you have to understand the ownership model quite well. If not, all the code you write will have compilation error. And ownership is just first part. After that, there's also this thing called borrowing, which is when you have a function that takes in a reference to an object, the function will borrow this object. Then it's not really moving ownership, but it is just borrowing the ownership. I forgot what the borrow model is already. So if you're interested, you should look at it yourself. But when I try to do the examples, it was a big pain. I get errors everywhere. I really cannot write this Rust. Okay, yeah. The summary is okay. Never mind. This is not for us. Yeah, there's no summary here. Never mind. Okay, so to summarize what we covered today, we look at other ways of memory management, which are so on one hand, we have the JavaScript engine that has garbage collection, but it is we might think that because the memory is managed by the runtime and not manually by us, we may not have bugs, but there may still be bugs in the underlying engine, underlying runtime or the GC itself. Now, on the other hand, we also look at this Rust that tries a different design, that sets very strict rules for the programs that you can write so that they can generate code that they can prove and confirm that there will never be any kind of use after free or double free. So as you saw here, we have not manually allocated any memory ourselves. At most, we try to create the object, but we did not need to do any manual freeing because Rust will check the scope and it will check the scope and do the freeing for us. So we don't need to do that. So it is also not exact. So the code that we try to write in Rust will be a bit similar to Java or Python that you don't need to free yourself. But the code that it generates is similar to C++ because it doesn't have a garbage collector, not like Java or Python. So quite interesting. That's why you see they all say Rust is the future, blah blah, and they I think Linux kernel people also want to rewrite in Rust, but I think maybe it's very hard. I think for systems, this C++ might still be nicer because of the flexibility that it gives. Rust, I don't know. I don't know. Maybe different people have different ideas. But I think Windows OS also, you say that they are rewriting certain things in Rust, which is good because it's Windows libraries a lot have bugs on. So maybe write with Rust, then it will be safer. Okay, that's all for this one. But some announcement for the future plans. So last week, Ting has asked in our Discord, he sent a poll about this group study for CodeQL. I'm not sure if everyone here is familiar with CodeQL, but CodeQL is a very powerful tool that is acquired by GitHub. So it's a bit like a SQL kind of language, but you query the code to do some static analysis mostly static analysis. We write some query to find certain code patterns. So for example, this query can find unsafe deserialization over here. So maybe some people are familiar with SamGrep, but CodeQL is more powerful than SamGrep because SamGrep in the end is just grep pattern matching on the okay, maybe they are not too different, But CoQL is more powerful because you can you can create very complicated queries that cover many rules. SamGrad, last time I looked at it, is simpler to use, a lot easier to use, but maybe not as powerful as CodeQL, especially for C++, at least. That's my experience. But CodeQL is quite hard to use. Look at all this. You need to learn to be able to know what to type. So the plan is, okay, so the reason for this suggestion is I suggested this to Ting because I I think I am running out of both energy to prepare because I got a bit busy, but more also because I think I'm running out of ideas of what to present already. I'm not very sure what to present already. So I think if we do this group study activity, we have many different things to cover. So the first step is we can follow these tutorials to learn the CodeQL ideas. And then there's one more here that teach some concepts like taint analysis, source and sinks, and then there's a lot of examples and explanations. Yeah, so there's so many resources that I think if we do this, we can do for 6 months or maybe 1 year, and we will do this at once every 3 weeks. So the plan is everyone will read one thing together. We will choose something to read and everyone will read together, and then one person will present, and then we will discuss. So not just one person presenting, everyone else, if you learn something new, you can also share. And then if you don't understand anything, you can ask, and everyone can discuss also. So like this, we can have different people involved with sharing, so that different people can try sharing here. And don't need to worry if you are not don't if you don't feel you are very good, because you can think of this more of just facilitating the discussion. Then if you don't understand anything as the presenter, other people can explain to you also. So don't worry. And if certain topic is very hard, we can do it slowly. We can read maybe the same thing. We can do certain exercises for 1 or 2 months. If it is harder and everyone takes longer time, that is okay also. Okay, so uh, yeah, that's all I have to say. Because the poll was accidentally made to be anonymous, so we also don't know who is interested. But I think we will start in first week of October, right?
Yeah, we can plan on that time.
Ah, okay, yeah, maybe we plan in
Okay.
Discord.
Yeah, I will need to summon the 12 persons first.
Yeah, yeah, we don't know who are the 12 people. Okay,
So yeah,
yeah,
that's it
then
for planning.
yeah, Ting has agreed to present for the first session, but don't we should not have the same person doing every time. We take turns so that we can share the workload also. Yeah, so after that we decide who are the next few people presenting. Okay, that's all. Thank you.
Okay, thank you. Let me stop the recording.
Okay.